Welcome to another episode of Radio Signals. My name is Mark, and my call sign is N9WIB. This is the Technician License Series, Lecture Number 12, Basic Radio Stages and Modulation. In this presentation, we'll review basic components of a radio or basic radio stages, as well as introduce the concept of modulation. And then we will define different types of modulation, including continuous wave, amplitude modulation, single sideband, as well as frequency modulation and phase modulation. The first stage we're going to cover is called the oscillator. An oscillator produces a signal at a specific frequency. It could be a very simple circuit or even a crystal oscillator. The oscillator is used to determine the operating frequency of the transmitter or receiver. In a transmitter, the signal generated from an oscillator is modulated or changed before reaching the antenna. Oscillators are present in both transmitters and receivers. After the signal leaves the oscillator, it can enter the driver or amplifier. The driver boosts or amplifies the signal from the oscillator to remain stable at low power. The output of the driver is applied to a power amplifier, which further boosts the signal so reliable communication can be achieved. At this point, the signal that reaches the power amplifier is fairly weak, so it needs a little more of a boost to be actually transmitted effectively throughout the air and heard by another station. A mixer is a stage that mixes or combines two radio frequency signals and produces a different frequency. So it'll take one RF signal at a certain frequency and take another at a different frequency and combine to make a different frequency. It's used in transmitters and receivers, but this is not the same as an audio mixer, which takes sound and combines them. It's an RF frequency mixer. And what we're most interested in this lecture is the modulation stage, or the modulator. A modulator adds information such as voice or data onto an RF signal or carrier. So the basic signal that's generated by the oscillator can be just a single tone. A modulator actually changes the RF sine wave in various ways, which we'll get into, to actually impart information onto that signal so it can be transmitted through the air and received by another station and then demodulated. So modulation creates information or adds information onto an RF signal, and demodulation decodes that information from that RF signal into the receiver. An unmodulated signal, as we learned before, just the base carrier signal, contains no information whatsoever. A signal's amplitude, frequency, and phase can all be modified or modulated to produce a data or voice RF signal. So as we learned before, a sine wave has amplitude or height. It also has frequency, how many cycles per second, and it also has phase, how the sine wave varies over time with respect to itself. So all those different components can be modulated to impart information onto the base carrier frequency. Bandwidth is how wide a signal is, how wide a radio signal is. Radio signals are comprised of a set of individual frequencies. They're not necessarily comprised of one frequency. The frequency you tune into your radio is essentially the center frequency, or what you're going to listen to. But that frequency is actually composed of a larger bandwidth. The range of frequencies is known as that bandwidth. Human voice on the radio ranges from 300 hertz to over 3,000 hertz. So that's 300 cycles per second to over 3,000 cycles per second, resulting in a bandwidth of 2,700 hertz or 2.7 kilohertz. This is a depiction of a typical AM radio signal. We'll get into this in a little bit later slides, but you can see that the signal is not just comprised of one frequency. It's comprised of a range of frequencies, and that creates the actual radio signal. In the center is known as the carrier, and you can see that either side of the AM signal is essentially a mirror image of frequencies. And both of those mirror images contain the same information. One of the simplest forms of modulation is called continuous wave, or CW. Many of you will be more familiar with this as Morse code. So continuous wave means exactly just that. It is a single frequency. It is, in its pure form, unmodulated. So that means there's no modification to the amplitude, there's no modification to the phase, or there's no modification to the frequency. However, it is modified in a certain way or modulated in a certain way by essentially turning the carrier on and off through use of a keyer. And again, this is known as Morse code. And this has a fairly narrow bandwidth of about 150 hertz. It's not the smallest bandwidth of the modulated frequencies, but it is one of the, it is not the smallest bandwidth, but is one of the smaller bandwidths. So I couldn't find an ideal drawing of what CW modulation is. So you've got to put up with my very basic artistry, if I can even call it that. So this is a typical carrier wave, the one up here. So we're going to call this an unmodulated signal. So UM for unmodulated. So this is essentially a signal that's been generated by the oscillator, be it a crystal or a small tank circuit, that is unmodulated. The frequency is not changing, the amplitude isn't changing, nor is the phase changing with respect to time. But as you can see, the modulated signal down here, so this is modulated, and it's the simplest form of modulation in that the signal is essentially turned on and off. So it's turned on for a period of time, which is this big dash down here, and it's turned back on for a shorter period of time, which is this period here, then turned off for another segment of time, and then turned back on. So this is a da, dit, and da, and this is actually the letter K. And this is, again, CW modulation, one of the simplest forms of modulation by turning the carrier either on or off at specified time frames. The next form of modulation is AM, or amplitude modulation. Essentially, amplitude modulation is adding voice or data to a signal by varying the strength or amplitude of a signal as a function of time. So you're just modifying the height of the sine wave or the strength of the sine wave over time. The frequency stays fixed, and AM has a much larger bandwidth than CW or continuous wave. The bandwidth for an AM voice signal is around 6,000 hertz or 6 kilohertz. AM signals are made up of three components. There's the center unmodulated carrier, and then the other two components are the lower sideband and the upper sideband. So it's essentially made up of two sidebands and an unmodulated center carrier. The sidebands are mirror images of each other, meaning they contain the same data as each other. And with this, AM has a better, more fuller audio quality than does other modulated signals. As we can see with this representation of an AM signal, there is a center carrier, and then there are two sidebands. The lower sideband is directly to the left of the unmodulated carrier, and the upper sideband is directly to the right. And if you look at the picture, the peaks and valleys essentially mirror each other to the right and left of the center line or the unmodulated carriers. They're mirror images of each other. They're symmetrical. They contain the same data. The top picture here is of an unmodulated radio frequency signal. With amplitude modulation, as we just learned, the amplitude changes. So the height of the sine wave or height of the RF wave changes over time. It can be higher, it can be lower, it can be taller, it can be shorter. Single sidebands in an AM signal, the carrier contains no data. Each sideband contains the same data as the other and are mirror images as we stated previously. Single sideband operation eliminates the carrier and one sideband. So as opposed to an AM signal, in single sideband you don't need the center carrier and you don't need either the upper sideband or the lower sideband. You're just going to choose one. Upper sideband or lower sideband may be used, but these are assigned to certain frequencies in amateur radio just based on convention. So one day, people just agreed that the upper sideband would be assigned to these frequencies and the lower sideband would be assigned to these other frequencies. A single sideband signal is much more efficient because power is concentrated into that single sideband. It has better propagation of signal compared to AM. So AM may sound better and more fuller, but a single sideband radio wave will go farther and give you better propagation. A single sideband voice is 2,000 to 3,000 hertz regarding its bandwidth. It is much more narrow. So it is essentially almost half of an AM signal because you're just taking one of the sidebands. And as we mentioned before, that the audio quality is less than that of AM, but the signal will get farther. And regarding the conventional naming of lower sideband or upper sideband with regard to frequencies generally below 10 megahertz in amateur radio, the lower sideband is used. Above 10 megahertz, upper sideband is used. There are a few exceptions. So, for example, on 60 meters or the 5 megahertz frequency range, the 60 meter band is channelized, which is one of the only channelized frequencies for amateur radio. And on those 5 channels, you're supposed to use the upper sideband. And on most HF bands, the data modes also use upper sideband regardless of frequency. And finally, regarding the basic types of modulation, there are frequency and phase modulation, and these can be considered at this point as one and the same. FM has a greater noise rejection with high audio quality, so frequency modulation or FM. PM is phase modulation, so again, think of it as frequency modulation as well. FM signals perform more poorly than single sideband or CW, and they're not a good option for weak signal propagation. They're primarily used for VHF and UHF on voice channels and also with packet. The FM voice bandwidth is from 10,000 to 15,000 hertz or 10 to 15 kilohertz. So it's a fairly large bandwidth modulated signal. It has larger bandwidth than AM, but the audio quality is better than AM as well. And another example for the signal modulation, the signal on top is the RF carrier or RF base signal, and it is unmodulated. The signal below is modulated with respect to frequency modulation. So the amplitude is not changing. The phase, we can't really tell if it's changing in this one, but essentially the frequency is changing. So it goes from a steady frequency to a higher frequency value, then back to a lower frequency value, then back again to a higher frequency value, and then back again to a lower. So this signal is being modified with regard to its frequency, and that's how the data is getting communicated. So now that we've covered the core group of modulation types, we can do a direct comparison of bandwidth. There are some data types that are much smaller than CW modulation, but let's just start off with CW first. So it's about 150 hertz signal, and then the bandwidth starts going up significantly. If we go to single sideband digital, it can range from 500 to 3,000 hertz, and single sideband voice, 2,000 to 3,000 hertz. And then, of course, if we go to AM, as we know, it's composed of the two sideband carriers, lower and upper. So you're going to double the single sideband voice bandwidth from 2 to 3,000 to around 6,000 hertz. And FM voice, for our concerns today, is the largest modulated signal that we're going to learn about, and it's from 10,000 to 15,000 hertz, or 10 to 15 kilohertz. So this was one of our shorter lectures during this series, but we hope you learned a lot. So we covered basic radio components or stages, and we also reviewed the concept of modulation, or how information gets transferred to a radio signal. And we reviewed many different types of modulation and how it specifically occurs, along with the concept of bandwidth. And we also assigned rough bandwidths to the various types of modulation and RF signals. So thanks again, and if you like what you're hearing and seeing, please consider supporting us on radiosignals.org, and we'll see you next time. 73. Have fun.